want to repeat the definition of upper limit and lower limit. Okay, it was denoted by mu and lambda. This mu was upper limit, this lambda was lower limit. Okay, so now okay, fine, Mappa. Actually, what I want is I want to make a soft copy of this whole book. Okay, make a PDF file of this whole book, but leave it. I will try to do that thing. It's okay. Okay, this mu was called upper limit and this lambda is lower limit. Okay, if I you know what do you mean a limit point? That every neighborhood of that point contains infinitely many point of the set. Okay, deleted neighborhood actually. Okay, so suppose this is mu. Okay, and this is the neighborhood, that is mu minus epsilon and mu plus epsilon. Okay, now what was the definition of upper limit? Was that for any epsilon greater than 0, the set has infinitely many elements. S has infinitely many elements greater than mu minus epsilon. So greater than mu minus epsilon, this side, okay, the set S has infinitely many elements. Yes, because if you check this neighborhood contains infinitely many points of S. That was the definition of a limit point. So obviously this area contains infinitely many points, that is which is greater than mu minus epsilon. So this was one definition, and another one was, and it has only a finite number of elements greater than mu plus epsilon. So this side, it has only finite number of elements. Okay, so infinitely many elements, this is okay, because this all elements is from this neighborhood. Okay, so it lies within the neighborhood and this neighborhood contains infinitely many elements. That's why there are infinitely many elements which is greater than mu minus epsilon. This is okay, but only finite over here. Why finite? Why not infinite? Okay, so this is the question. So why not infinite means, if instead of finite it is infinite, okay, there are elements which is greater than mu plus epsilon, there are infinitely many elements, suppose, then what happens, there will be some element which is greater than mu, okay, there is one element over here. Let us suppose that this is mu1. Okay, in at this point there's one element mu1. Then if you make a neighborhood of this mu1, then this mu1 will also contain infinitely many points. Okay, because greater than mu plus epsilon there are infinitely many elements. So in this area there are infinitely many elements. Okay, we have supposed that. That means this mu1 over here, which is greater than mu, okay, because this side it is greater than mu, also contains infinitely many elements. Neighborhood of this mu1 also contains infinitely many elements. That means this mu1 is also a limit point which is greater than mu, which is impossible because mu is the greatest limit. Yes or no? According to the definition, mu is the greatest limit point. Okay, that's why there is only finite, not infinite, which is greater than mu plus epsilon. Is that clear, everyone? So this was the definition of upper limit mu. Similarly, lower limit when this is lambda, this is lambda plus epsilon, and this is lambda minus epsilon. So greater than lambda minus epsilon, or okay, less than lambda plus epsilon. Okay, not greater than lambda plus epsilon, but less than lambda plus epsilon. There are infinitely many elements of S. Okay, because it is within the neighborhood. Clear? But less than lambda minus epsilon, it is finite, because if infinite by again ke huncha, we'll find another lambda 1 whose neighborhood also contains infinitely many elements, which is a contradiction because lambda is the least limit point, not lambda 1. Is that clear? That's why elements which is less than lambda 1, there are only finite many elements, not infinite. Clear? So this was the definition of lower limit and upper limit. So if you understand why all these things are done greater than less than, then it will be easier for you to remember the definition every time. Okay, upper limit when secure, you can understand. Okay, so there are a lot of examples and exercises also to find out upper limit, lower limit, and supremum and infimum also. Okay, this is M, this is M. Okay, this is the bounded set on the infinite bounded set on the, that's why there are infimum and supremum bounded and there is always least limit point and greatest limit point, lambda and mu of an infinite bounded set, according to the Weierstrass theorem. An infinite bounded set always contains a at least one limit point. Okay, lambda and mu. Okay, now m is always less than equal to lambda, less than equals to mu, less than equals to m. Okay, lambda and mu can be equal sometimes. Okay, there's one example. Okay, यो छ मैले last time पनि गरे, set s is equals to 1 by n belonging to n. Okay, can you tell me the infimum and supremum of the set? Anyone? What will be the infimum and supremum of the set? Anyone? You know what do you mean a supremum and infimum?
So supremum 1, infimum 0.
Yes. Supremum is 1 and infimum is 0 because n belongs to n. If n tends to infinity, 0. 0 the many elements you will never get. Okay. And if you n belong to n, that means 1 is the smallest point of this set. So if you put 1, then it is 1. So all the elements inside S is always less than n and greater than 0. So suppose x belongs to S, then x always lies between 0 to 1. Okay, so infimum is 0 and 1. Okay. Now what is lambda and mu? Lambda means lower limit, upper limit. Okay, I will rub part. So it is very much easier if you draw a graph. Simple real line though, so just draw a graph. Okay, so it starts from, okay, one thing students, suppose this is 1. Okay, and this is 0 because supremum and infimum is 0 and 1. Now if you put n equal to 2, it is half. If you put n equals to 3, it is 1 by 3. So यो जुन चाहिँ बिचको डिस्टेन्स चाहिँ घट्दै 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 जान्छ हैन. Okay, wait, अलिकति यता गरौँ. 1 equals to 3, 1 by 4, 1 by 5, 1 by 6, 1 by 7, 1 by 8 with this कहाँ जान्छ? Actually comes to 0. Okay, now okay, it is like 1, okay, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, it goes on, 1 by 100. Okay, now 1 cannot be the limit point because if you draw an neighbor within 1, then you will never get an infinitely many points within this 1. Half is also not possible because inside half you never find a neighborhood of half, you will never give a infinitely many points. Okay, similarly 1 by 3 पनि हुँदैन, 1 by 4 पनि हुँदैन, 1 by 5. Okay, if you take a 1 by 100, this is also not possible. Okay, so the only limit point, the only point whose neighborhood contains infinitely many points is 0. Okay, so if you take epsilon, epsilon minus 0 comma epsilon plus 0, so this is nothing but epsilon comma O. So if you take 0 minus epsilon comma 0 plus epsilon, the neighborhood of 0. So minus epsilon comma epsilon. So since epsilon is always less than 1 by n, okay, it is very small number. Epsilon is a very small number. Okay, so this neighborhood, since epsilon is less than 1 by n, okay, so this neighborhood contains infinitely many points of this set S. Okay, so that's why only 0 is the limit point of this set. So in this case, lambda is equals to mu equals to 0. Is that clear? So this is the definition of lower limit and upper limit. Okay, now we'll step. Okay, do you have got anything to ask? Kesa sodhnu parne? छैन हैन? So you just study and try to solve the exercises, and if you face any problem you can just ask me. Okay, the main thing is you will get the questions like find the infimum, supremum, least limit point and greatest limit point. This type of questions you will get from these chapters. Okay, and also some theorems. Okay, now we'll start a new chapter, sequence of real numbers. Okay, this is a huge chapter. I think this is your second last part from the syllabus. Okay, and after this you have got only series and series basis scenario. Okay, you have got only few topic from sequence. Okay, series. Okay, how you define a sequence? First is it is a mapping x from n to r. Okay, you know what you mean a mapping. So n means set of natural numbers, r means real number. So you will get x of, suppose small n. Okay, n belong to n equals to xn. Okay, which belongs to r. So this is the definition of a sequence. So it is a mapping x from set of natural numbers to r. Okay, and this, what is this xn? This is the image of this small n. Okay, now so this image of n is denoted by this xn. Okay, so our sequence is nothing but like this: x1 comma x2 comma x3 comma, in this way. Okay, and these are all real numbers. Okay, suppose you have got a finite sequence. Okay, so this 3 is x1, this 5 is x2, this 7 is x3. Okay, and these are the terms: first term, second term and third term of the sequence. Okay, you have got also a infinite sequence of positive integers. So what is the infinite sequence of positive integers? This is 1 2 3 4 . So this is x1, this is x2, this is x3, this is x4. So this is an infinite sequence of positive integers. Okay, so there is also an infinite sequence of odd integers, and always sequence is written in this form within the curly bracket. Okay, so sequence of odd integers x 2n minus 1. So in this case xn is 2n minus 1. This n belongs to n. Okay, so in this case if you write in terms of a mapping, then x of n is nothing but 2n minus 1. Okay, so just put n equals to 1. Okay, that is n belongs to n. Starting from n belongs to 1, then 2 minus 1 is 1, 4 minus 1 is 3. So this is sequence of odd integers: 5 7 9 11. Is that clear? So this is the sequence of odd integers. Okay, we have also got the harmonic sequence. Harmonic sequence is 1 by n. Okay, 1 half, 1 by 3, 1 by 4, 1 by 1 by n. Okay, this is called the sequence of harmonic sequence. Nita? बाहिर लक गर छिटो न हौ बाहिर लक गर न Okay, there is another sequence. Okay, these are all the examples of a sequence. Okay, I'll just send you the PDF file of the sequence chapter. You can just go through it and just check all these examples. Okay. Okay, there are also sequence like this. Okay, and this one important one. Minus 1 all to the power n minus 1. Okay, so this is nothing but 1 minus 1 1 minus 1 1 minus 1. Okay, and this goes on. Okay, so this you will also get sequence of this type. Okay, I think this is enough for you all. Okay, one constant sequence where there is a constant sequence. Okay, every term is equals to 4. So this is how you write the sequence. Next one, bounded sequence. Okay, this is the same as bounded set because if sequence is bounded, then it is bound from both the left side and right side with one upper bound and one lower bound, also called infimum and supremum. Okay, okay, xn is bounded above or bounded below according as the range set of xn is bounded above or bounded below. So in this case, the sequence xn is bounded above and bounded below both. Okay, so a sequence is said to be bounded above. Okay, if the sequence is said to be bounded above, if there exists a real number u, okay, if there exists a real number u such that this xn is always less than or equals to u. What is this xn? These are the elements of that sequence. Okay, for all n belonging to n, and this u is called the upper bound. Is that clear? So all the members of that sequence is always less than or equal to u. That means u is the upper bound. Okay, and it is said to be unbounded above if there exists at least one member of the sequence xp. Unbounded above, there exists at least one member xp of the sequence such that xp is greater than g. Okay, for any given g greater than 0, so xp is greater than g, that means g is not the upper bound. Clear? So this is the definition of bounded above and unbounded above. Similarly, bounded below ko लागि चाहिँ के हुन्छ भन्दाखेरि there exists a real number l such that xn exists a real number l such that xn is always greater than or equals to this l for all n belonging to n. So this l is the lower bound. Okay, but if it is unbounded below, then for given any g greater than 0, okay, such there exists at least one member xk. Okay, there exists at least one member xk which is less than minus c. Okay, so okay, screen. Okay, so xk is less than minus c. That means um, this side you will get upper bound u, and this side you will get lower bound l. So the members will be lie between this. So xn is always less than u, less than or equal to u, and xn is always greater than or equals to l. Okay, and if it is unbounded, then you will get some g over here, which is less than some members of at least one member of the sequence, and g you will get g somewhere over here where xn is greater than g, or xk is, if I write minus, then you'll get xn. So minus xn means, okay, let us suppose that this is some xk which is less than minus c. Is that clear? So this is the definition of upper bound and lower bound. If these definitions are satisfied, then you see that the sequence is bounded above. Or you can also write, if a sequence is bounded, then it is both bounded above and bounded below. Then there exists a positive number k, such that for all n belonging to n, mod of xn is always less than k. So this can be written as minus k less than equal to xn less than equals to k. So this is the definition of a bounded sequence. Is that clear? So now, if the sequence xn is bounded above, okay, then you know the LUB axiom. If it is bounded above, okay, then there exists a real number m called the supremum. That means the supremum exists, and you know the definition of supremum, that is it is the least upper bound. All the upper bound, suppose there are set of upper bound, okay, the smallest upper bound is the supremum. Okay, so for all n belonging to n is xn is less than equal to m, that is it is the upper bound. Okay, and given any epsilon greater than 0, there exists at least one member of xn, say xp is greater than m minus epsilon. So that means this is m, this is small m. So xm is always it is an upper bound. Okay, that means all the members are less than m, and if you just subtract small number epsilon, okay, m minus n, then there you will get at least one member such that this is less than that member. Okay, that means this is the least upper bound. Okay, if you get the set of upper bound, then the least one will be your supremum. Okay, similarly for infimum, the definition is it must be infimum, that is xn must be greater than equal to m. First part is this, and second part is if you add m plus epsilon, then this m will just move a little bit. Okay, you move epsilon distance, m plus epsilon, then there will you will find some elements in between this, okay, xp, which is less than this m plus epsilon. Okay, this xp is less than m plus epsilon. So these are the definitions of supremum and infimum. Is that clear? So you just don't forget what is supremum, infimum. Okay, upper limit, lower limit, up bounded above, bounded below, upper bound, lower bound. Okay, they all have their own properties, so you should remember that. Don't mug it up. Try to understand what are all those things. Okay, if you are clear about those things, then you don't have to um, uh, mug it up everything else. Okay, so there are examples also. Okay, I'll just send it to you, just check it out. Okay, all those examples, I think you can. If you don't understand, then you can ask me. Okay, next is monotone sequence. Monotone sequence means the sequence, some sequence are increasing, some sequence are decreasing. Like set of natural numbers, it is monotonic increasing, 1 2 3 4, it is increasing sequence. Okay, and the harmonic sequence 1 by n, it is monotonic decreasing sequence. Okay, so in definition, a sequence section is said to be monotone decreasing, monotone increasing, sometimes called non-decreasing also. Okay, monotone increasing. If xn plus 1 is greater than xn, okay, xn plus 1 is greater than equal to xn, that is second member is greater than first member. Okay, so and you know the definition also. Okay, and sometimes it is strictly also strictly monotone increasing. Okay, in that case you will get xn plus 1 strictly greater than xn. Okay, the sequence, the members are strictly greater. Okay, similarly monotonic decreasing, that is xn plus 1 is less than or equal to xn, that the first one is greater than second, second is greater than third, third is greater than fourth. Okay, so in this case the harmonic series 1 by n is monotonic decreasing, and sometimes it is strictly also. Then xn plus 1 strictly less than xn. Okay, so this harmonic series is also strictly monotonic decreasing. So a sequence section is said to be simply monotone if it is either monotone increasing or monotonic decreasing. If xn is monotonic increasing, then minus xn is monotonic decreasing. Okay, so there are a few examples of monotonic increasing and decreasing. Okay, we have got the sequence. Suppose 1 1 2 2 2 3 3 3 3 4 4 5 6 5 5 6. Okay, this is monotonic increasing sequence, but not strictly monotonic increasing. Is that clear? This is just simply monotonic increasing, not strictly. Okay, so this is how you define. Sometimes you will get sequences which is neither monotonic increasing nor monotonic decreasing, that is it is not a monotone. Okay, the this example minus 1 to n minus 1 minus 1 1 minus, it is neither monotonic nor monotonic decreasing. Clear? Okay, now next is limit of a sequence. How you define limit of a sequence? You know what is a limit? Okay, from your plus 2 level you know how you define a limit. Okay, limit is that number where the given function approaches to that point, not exactly equal, but it is approaching towards that point. Okay, that is the limit. Okay, so in this case also the same thing. Sequence xn of a real number is set to tend to a finite real number l. Okay, it is approaching, tend to means it is approaching towards that finite real number l. Okay, if and only if for any given positive number epsilon, no matter how small, that means that epsilon must be very small number, there exists a positive integer n naught, such that for all n greater than equal to n naught, the inequality xn minus l less than epsilon holds. So for epsilon greater than 0, this is a very small number, there exists a number n naught, positive n naught, such that for all n greater than or equal to n naught, the inequality xn minus l less than epsilon holds. Okay, so what does this means? For epsilon greater than 0, there exists n naught. For all n greater than equal to n naught, xn minus l less than epsilon holds. So this means that suppose this is the this real line, because sequence is nothing but it is the real numbers. sequence of a real numbers, right? X is a mapping from n to r, so xn is belonging to r. So let us suppose that this epsilon is a very small number, one thing. Okay, this is a real line of xn, x1, x2, x3, x4, so it goes on. Okay, now for all n greater than, suppose this is the point n naught anywhere in the real line. So whenever n tends to infinity, okay, whenever n tends to, so n tends to infinity, xn tends to L1 actually this limit, okay, this whole thing. So whenever n tends to infinity, so that means n is greater than equal to n0, that is n is greater than n0. So all the values which is greater than, just take any number n0 in between, okay, you can take anywhere else. Okay, so whenever this n is greater than n0, so that means n is going towards this side. So n tending to infinity is defined in this way, in definition, n greater than equal to n0. So n is increasing, okay, that it is going towards infinity, it is increasing, okay, every time it is increasing. That's why n is greater than equal to n0. When n increases, okay, then the differences of this xn minus L less than epsilon x, the difference of this xn minus L is very small. This differences decreases, that means, okay, that means if I write in this, if I remove this mod, then you will get L minus epsilon is less than xn is less than L plus epsilon. That means whenever you go to the neighborhood, this, suppose this is L, this is L, then this neighborhood is L minus epsilon and L plus epsilon. Then this xn lies in this neighborhood when n is very greater. Okay, it increases towards infinity. Whenever n goes towards infinity, it is increasing. N is greater than equal to n0. Okay, then this xn lies in this interval, that is the neighborhood of epsilon, neighborhood of L. Is that clear? So this is how you define limit, mathematically or just simply in a definition. So this you can write limit n tends to infinity, xn is equals to L. Okay, so symbolically epsilon greater than 0, there exists n0 belonging to n such that xn minus L is less than epsilon for all n greater than equal to n0. Okay, now a sequence xn is said to be convergent. Now after definition of limit comes the definition of convergent. If there is a limit exists for a sequence, then we say that sequence is convergent, converges to some point. Okay, you know what do you mean a convergent. So a sequence xn of real numbers is said to be convergent if it has a finite real number L as its limit. So whenever a sequence converges to some limit L, then we say that the sequence is convergent. So xn converges to L implies n tends to infinity, xn tends to L. So this means sequence xn is convergent, and if it does not converge to any limit L, then it is divergent. Okay, divergent definition, you will have 2-3 definitions of divergent. Okay, not only it is not convergent, you can say it is divergent. Okay, we'll come to that later. So this is how you define a limit and a convergence. Okay, I will do one this theorem, then I think we can stop here for this today's class. This limit of a sequence is always unique, remember that. Okay, a sequence xn of real numbers can have at most one limit, not at least. Okay, so don't get confused about at most and at least. So the limit is 1, either 1 or no, either 0. Okay, so let us suppose that the sequence has two limits. So xn tends to L and xn tends to L dash as n tends to infinity. There are two limits. Now we have to prove that this L and L dash are equal. Okay, then from the definition we can say that this xn minus L is less than epsilon by 2 for all n greater than equal to n0 or n0 dash Okay, and xn minus L dash is also less than epsilon by 2 for all n greater than equal to n0 double dash. Let us take the maximum of n0 dash and n0 double dash. Since both are n greater than n0, okay, यो n0 भयो अरे यो भन्दा ठुलो भन्दैछ, this is n0 double dash greater than n. So let us take the maximum one. If we can take the maximum, then this definition is valid for both. So if n is the n naught is the maximum, then take n greater than equal to n naught, and this also n greater than equal to n naught. So this both the definitions are valid for n naught. Okay, then we can write mod of L minus L dash is equals to L minus xn plus xn minus L dash. So this is nothing but less than or equals to L minus xn plus xn minus L dash. So this is nothing but xn minus L, they are same. So this is less than epsilon by 2 plus epsilon by 2, which is equals to epsilon. So mod of L minus L dash is nothing but less than epsilon for all n greater than n naught. So that means L and L dash are equal. Okay, L minus L dash less than epsilon means whenever this n reaches to infinity, this L and L dash become same. Okay, so this is our proof that limits are unique. The convergence sequence determines its limit uniquely. Okay, there are few examples of convergent sequences. Okay, I'll just send it to you all, just check it there. Like the harmonic sequence. Okay, the harmonic sequence always converges to 0. Okay, just check all these examples. Okay, from next on we'll start with the convergence sequence. Okay, limit definite theorems on convergence sequence and all. Okay, so for today class I think we can stop here. Do you have got anything to ask? You can ask right now.